Hello, welcome to physics. We've been studying waves, which as you know are disturbances caused by vibrating particles which send energy from place to place. Our most recent topic has been refraction, which is where light waves encountering a change in medium change direction. We've learned a qualitative look at that. Today, let's get some numbers in here. Alright, so first of all, you know we have this concept called c, the speed of light. 3 times 10 to the 8th meters per second. So fast. That's the speed that light moves in a vacuum. And in a vacuum, every kind of light, all frequencies of light will travel at that exact same speed. However, light does slow down, as we know, moving in different materials. And in particular, different frequencies of light would be affected more or less by different materials, so they slow down differently depending on their frequency. So what? So what does that mean? Well, if you have a chunk of glass and you throw some normal sunlight in it, sunlight being white contains all colors of light, you'll see as that light passes through the glass, it bends, and each shade of light bends slightly differently, and it's going to throw a rainbow out at the wall. How cool is that? Speaking of rainbows, a question people often ask is, what's at the end of the rainbow? Well, here comes physics to ruin that. Guess what? There's nothing, because there is no end. Every rainbow is a circle. Did you know that? Go high up enough that it doesn't intersect the Earth and you'll see it clearly. Beautiful, isn't it? So for the quantitative part of today's lesson, we're going to look at something called the absolute index of refraction, which is a handy shorthand way to say, how fast does light move in this particular material? Absolute index of refraction is given by a small letter n, and it is expressed as a ratio of the speed of light in a vacuum over the speed of light in that particular material. Please note, nothing in the universe can ever move faster than c, the speed of light, so this ratio will always give you something greater than or equal to 1. Remember that this is basically an expression for how much that speed is different than the speed of light. So the larger the number is, the slower the speed. Here are a couple examples to show you how this might look. These are the same concepts as what we've looked at before, where we said something would slow down or speed up. We're just attaching some numbers to it now to represent that. So the first example on the left, you have light moving from a medium of lower index into a medium of higher index. It's going to slow down, which means it's going to bend towards that normal line, as you can see on the left. On the right-hand side, it's reversed, where the light is going to speed up as it leaves that material. The n gets smaller, and you can see that as that angle getting larger, the light bending away from the normal. Now, you might be finding yourself saying, all this talk of bending towards or bending away is very good and all, but I really wish we could be a little more precise than that. Well, worry no more. I present to you today Snell's law. Snell's law is a nice way to quantify what we've been talking about all along by relating these four properties together. On the left-hand side, we have n1 sine theta 1. N is, as we just learned, the index of refraction for that first material, the material that the incident ray is in, and theta 1 is the incident angle, the way that it strikes that surface, measured down from the normal line as we've been doing. On the right-hand side of the equation, it looks the same, n2 sine theta 2. So again, we're seeing if the material itself is changing, and that's reflected in the different n, and then that will show you a different angle in that material, and that's reflected as theta 2. Those two things are going to be equal to each other, the product of the index of refraction and the sine of the angle of incidence, both in the first material and the second. One outcome of this change of angle is what's called the critical angle. And that's the idea that if light is traveling through a material where it's moving slower, and it's trying to exit to a faster material, as that angle gets bigger and bigger and bigger, there's a certain point where it's so big that the refractive angle, the second angle, is 90 degrees, which means it can't leave. It's stuck inside the first material. There's no exiting. This is called total internal reflection. And anytime the incident angle is larger than or equal to the critical angle, you'll find this happening. This is a principle that's used to make fiber optic cables. If you don't know, a fiber optic cable is basically a piece of glass that's a millimeter wide and thousands of miles long. So somebody in, say, Europe can shine a light into one end of this fiber optic cable, and the cable goes all the way across the Atlantic Ocean and comes over here to us, and the light comes out the other end. How does it do that? Well, it does it because glass slows down that light, and the angle that they shoot it in at is larger than the critical angle, so there's total internal reflection every time it hits the side, and it just ricochets around in the glass from one end all the way over to the other. Cool, huh? If you swim a lot, you've probably also noticed this. Check out this image from underneath the surface of a pool. Wait, you can't see out. Why can't I see out? I'm not going to tell you the answer, because I think you can figure it out yourself. You're so smart. So that's a look at refraction and Snell's law today. Thanks for watching. I enjoyed learning physics with you.